So, can you see my screen?
I can, sir.
Good. According to what we have here, a relation is a generalization of a function. I think you should mute your mic until you need to say something. All right, good. So a relation is a generalization of a function, and a function, something that relates, one set with another set. So the word relate, come from relation. So we have set A and set B. A relation just tells us a rule that maps one element in set A to another element in set B, and it is a subset of the cross product. I mean the product of two sets. If I have sets 1, 2 and sets A, B, C, do you know what their product is?
Yes, sir.
What's it going to be?
I have 1A, 1B, 1C, 2A,
Good.
2B, and 2C.
Good. So this is the cardinal product, Cartesian product. And the relation is any subset of this cardinal product. So you will always have something in the set A and something in the set B. So a function is just a special type of this kind of relation where we know that for every first element, I mean the element in the first set, there is only a unique element in the second set. So it is a binary operation because you are looking at just A and B. So when you're talking about relationship, it is not something within two or three or more parties. It's just between two parties, two sets. And that is why we have the binary relation here. So we have a pair, A comma B, which is telling us that A is related to B. And with the following statements. So A is related to B. We write it this way. Some people write it this way. And A is not related to B. So the symbol is missing. So it should be A is not related to B. All right. So like I said, it is a subset of the Cartesian products A and B. And the set inclusion is a relation in any class of set. So when you have, because we could talk about different kinds of objects that we want to relate to each other. And one of the common ones are the sets. And in any in any class of sets, the set inclusion is a good example of a relation. So we could actually use the analogy of a family. So, or when you have a group of people, they can be related as and you can say he is my relation. He is my relation. He's my brother and my sister. So we can define relation in terms of whether you are blood related or whether you are related by the club you support, whether you are related by the religion you follow. These are kinds of relation. So when we have sets as well, we could use set inclusion. We could use equivalence of sets. We could use cardinality of sets. So I can say two sets are related when they have the same cardinality. I can say two sets are related when they are equivalent. You know the difference between equal sets and equivalent sets?
Yes, sir.
So what's the difference?
Equal set means the set contains the same element, no matter the order of arrangement. While equivalent set talks about their cardinality.
Good.
Let's say set A contains elements, set B contains 5 elements, so set A and B are equivalent.
Good. Good. That's the idea. Very good. So A and B could be related if A is a subset of B or B is a superset of A. Then if we could also talk about the parity of integers, we'll talk about the natural order in integers. So if we say this is set A and this is set B, we can use the less than or equal to order and say something in A is related to something in B if and only if A is less than B. So what are going to be the elements of this relation? Can you tell me the elements of this relation?
A is less than B, right?
Yes.
That's 2, 4, 2, 4,
Mm-hmm.
2, 6, 3, 4, 3, 6, then 4, 6, and then 5, 6.
Okay.
4, 6, and then 5, 6.
Beautiful. Beautiful. So that is just the general introduction to relations. And the domain of a relation from A to B is just the element, the first element that you see in the pair, while the range is the second element that you see in a pair. So for instance, in this relation, what's the domain? The one we did up here. So if I call this R, what is our domain of R?
That's 2, that's 2, 3, 4, 5, 6. Any element from there.
Are you sure 6 is there?
No.
Good. So it's
Sorry.
just 3, 4, 5.
Yes, sir.
What about the range?
That's 2, 4.
Are you sure?
2, 4, 6. Rather 2, 4, 6.
Are you
From there,
sure?
2, 4, 6. Yes, sir.
Are you sure?
Oh, sorry, sir. Sorry, let me confirm. That's 4, 6. Yeah, 4, 6, 4, 6, 4, 6 only. I was just looking
4,
at the main
6.
set. I was not looking at the Cartesian product.
Okay. So it is not, don't forget, it is not the Cartesian product. It's a subset of the Cartesian product. So every relation is a subset of the Cartesian product used, which we build with a particular rule. In this case, the rule is the set order, less than. Good. And it has to be strictly less than. Assuming it is less than or equal to, then it is almost going to be if not all, it's almost going to be the Cartesian product. All right. So the domain of R is always a subset contained in A, while the range is contained in B. Good. I hope that statement is clear.
Yes, sir.
So domain of R here, we can see that it is a strictly contained in A, just as the range of R is strictly contained in B. Then when we are talking about inverse of a relation, all we just need is to flip the elements of the relation. So as the example we started with, what is going to be the inverse?
I'll be sorry, sir. I'm low. Sorry, sir.
Yeah, okay.
I'll be 4, 2,
4, 2,
6, 2, 6, 2,
6, 2,
4, 3,
4,
4,
3,
3, 6, 3,
6, 3,
6, 4,
6, 4,
and 6, 5.
and 6, 5. This is the inverse of that. Then if two, oh, I didn't even know that these are here. So that is the exercise we've just completed. So if two relations are such that for each element in the domain, their images are the same. So if you have two relationships and you have that for each element in the domain, they have the same images, then we say that those two relations are equal. And I hope you know what the meaning of image is.
Yes, sir.
Good. So that is clear. We can now go on to what is here. So the concept of relations on the set of integers. This is just a generalization. Relations can happen on any set, but most of the relationships you would come across, most of them at this level, they are going to be that on integers. So when we say AR1B, we are saying A is less than B. Now when we say AR2B, so these are different kinds of relations. Okay?
Yes, sir.
So AR1B means A is less than B. So we could have something like 2, 5. We could have something
Yes,
like
sir.
-1, 0. These are examples of elements in R1. So can
Yes,
you give
sir.
me 2 examples of elements in R2?
I will have to like do the what's it called? Write it in my notes, but I not take the note down, so it won't be slow. Let us write out the element of A and element of B. That's
No, you cannot. It is not possible to even write the element of A and B here. Not possible. We are dealing with the set
yes,
of
sir. Like
integers.
I've not done the Cartesian product yet. I don't write it down in my notes. So I don't have it in my notes.
What I'm saying is you could actually just look at this and give me 2 examples of elements in R2 if you understand what the description of the elements are. So the description is saying 2 elements are related if their sum is greater than or equal to 5.
Yeah, 5. Yes. We have 2
So
and 4.
2, 4, good,
2, 6.
and so on and so forth. I can have
Yes, sir.
-7,
Yes, sir.
15. Okay, so these are elements of R2. And what about R3? Can you give me elements of R3?
That 2, 4. 2,
Are you
4.
sure? Are you sure?
Yes. A equals to, no, sorry, sir. 4, 2 rather. 4, 2.
4, 2,
4, 2. Can have -3 and -6.
Is that correct?
Can have, yes, -6 and -3.
-6, -3. This is in R3. Good. What about R4?
That's 2 and 4. Can have 3 and 5.
Good. That takes us to reflexive. Reflexive, so there are some properties of relations that are very important in classifying relations. The first one is reflexivity. We have, let me list the important ones. We have reflexivity, we have symmetricity, we have before transitivity, let's write anti-symmetricity. We have transitivity. Yeah, these are four very important properties of relations that helps us to classify relations into ordered relations or equivalent relations. Okay, so the first one, reflexivity. A relation is said to be reflexive if for any element of the domain we have that element is related to itself. Okay. Are you still there? Hello?
Sorry for the interruption, sir. My phone just went up on its own. Or it was showing me a battery or something like that. Then I know it went off by itself. But it's back on now, sir.
Okay. So
Sorry
as
for
I
the
was saying,
Yes, sir.
a relation is said to be reflexive if for every element in the domain, that element is related to itself. That is reflexivity. So
Your phone is not showing now.
my screen is not showing.
Okay, it is now. It is now.
Okay. So a relation is said to be reflexive if for every element of the domain, the element is related to itself. That is the simple way of describing what
Uh,
reflexive
activity.
is. Good. So let's come back to R1. Do you think R1 is reflexive?
Oh no, sir.
Why is it not reflexive?
Because we have two and negative one. We have two and for from the vision of reflexivity, where instead it's said to be reflexive if it is related to itself. But two and minus one, they are not related.
That is not the way to explain why it is not reflexive. So if you are to show a counter example, because the counter example is enough to prove that something is not reflexive, you have
Yes,
to
sir.
show that you have to argue that A comma A is not related to A. Okay, so not two and negative one, but you have to show that 2 comma 2 or you have to say that 2 comma 2 is not in R1. Do you agree that 2 comma 2 is not in R1?
Yes, sir.
So why is 2 comma 2 not in R1?
Because 2 is not less than 2.
Because 2 is not less than 2. Beautiful. What about R2? Is R2
R
reflexive?
R2, no, sir.
Why?
Same thing here.
2 comma 2 is not in R2.
Yes, sir.
What about R3? Is R3 reflexive?
No, sir.
Again, 2 comma 2 is not in R3. What about R4? Is R4 reflexive?
R4, yes, sir.
Why is it reflexive?
Because 2 and 2 have the same parity. So
Now, if you want to show that something is truly reflexive, you cannot use a number. Because if it is true for 2, what about 3? What about 4? What about 5? Okay, so you only use specific numbers to show that something is not true. Okay? But if you want to show that it is true, you have to generalize it. And in this case, you can just say every integer has the same parity as itself. Okay? For any integer A has the same parity as itself. Therefore, A is related to A under R4. Therefore, R4 is reflexive. That's a 3-line proof or 3-statement proof. Okay? Okay. If your friend is also disturbing me for relation,
okay.
let me see if I can just send the link to him. You know who I'm talking about, Abi?
Adams?
Yes.
Be active.
Let me just send it to him if he can join. If he cannot join, Olomo. All right. So R4 is reflexive. Good. So the next one is symmetric. So you understand reflexive property now, right?
Yes, sir. Yes, sir.
The next one is symmetric. A relation is on a set A is said to be. So when we say reflexivity, it's usually on one set. Okay. It is not, generally we have defined relation to be something between a set and another set, right?
Yes, sir. Yes, sir.
But when we are talking about reflexivity, when we are talking about symmetricity, we are talking about on just one set, in relationship between a set and itself. Okay?
Yes, sir.
So when we say a relation on a set A, so we are saying the domain is A, the codomain is also A.
Yes.
So a relation on A is said to be symmetric if anytime, you have to be very careful, if it doesn't say that for all A, B. It says that anytime A is related to B, we must have, if A is related to B, then we must have B related to A as well. Okay?
Yes, sir.
So if A is related to B, we must have B related to A. It is not in every set that two elements can be related. That's another
Yes.
property on its own that we call comparability. A set is said to be comparable if any two sets can be compared, if they are related. So if you want to look at symmetricity, you only look at the elements that are related. So if A is related to B, it is not always true that B is related to A.
Yes, sir.
So if A related to B and B related to A in all cases, then the relation is said to be symmetric. So let us now go through our usual R1 to R4.
Okay, sir.
So you remember R1. R1 is
Yes.
about less than. So is R1 symmetric?
No, sir.
Why is it not symmetric?
Because for A related to B does not imply that
If
B is related to
again, remember that when you want to say something it does not satisfy a property, you just need to show a counter example. So you can use numbers.
Okay, sir.
So you can say R1 is not symmetric because 2, 5 is in R1, but 5,
5.2.
2 is not in R1. What if I
Okay,
change
sir.
it to less than or equal to?
Less than
Will
or
it be
equal.
less? If I change it to less than or equal to, so let's say R5.
Okay.
A R5 means A is less than B, less than or equal to B. Let's start with
So
reflexive. Is it reflexive?
yes. No, sir. Less than or
Are you
equal.
sure
Yes,
it's
sir.
not?
Yes, yes, it is.
Are you
Yes,
sure?
it is reflective. Less than or equal to it's reflexive.
It is
It is.
reflexive. Good.
Yes,
It
sir.
is reflexive because every integer is
It's less than
related to itself.
or equal
It's less than or equal to itself.
to itself. Yes, sir.
Is it symmetric?
No, sir. No, no, no. It's not.
Can you give me example? Can you give counter example?
Okay, sir. Let's say we have the same 2 and 5.
Good. 2 is less than or equal to 5, but
5 is
5
not
is not less than or equal to 2.
equal to 2.
Okay, so see, when we changed the relation a little bit, it became reflexive, but it still is not symmetric.
Symmetric.
Okay?
Yes, sir.
Yeah, Adam said he would join in a bit.
2 points.
So let's go to R3.
Okay, sir.
Is it symmetric?
Out for 2. No, sir.
Why is it not symmetric?
Okay. So we have are we dividing with R5? A less than or equal
No,
to B.
R2.
Out.
These are R2.
Okay, sir. So I have 2 for no.
If people,
Out,
if
out
people,
is not.
if people hear me shouting R2, they will think I'm playing PS. So yeah, so
we
is
have
it symmetric?
we have what's it called 2 4. 2 4 is defined on R2, but 4 2 is not defined on R2, so it's not
R2
symmetric.
is not an element of R2, so it's not symmetric. Good. What about R3? Is symmetric?
I have 4 2. No, sir.
Good. Why?
Because 4 2 does not imply 2 4. 4 2 is defined, but 2 4 is not defined on R3.
R2 is an element of
R,
R3,
okay,
but
sir.
2,4
I
is not
4
an
is defined.
element of R3. So relation is a relation is a set. It's a
Yes,
subset
sir.
of the Cartesian product. So we can say element of, okay?
Yes, sir.
Good. What about R4? Is it symmetric?
No, it is not.
Eh?
2 4 is an element
R4.
of 4.
Look at R4.
Yes, it is because 2 4. Same parity, you have 2 4, you have 4 2. Yeah, it is. Because 2 4, 2 and 4 has the same parity, then 4 and 2 has the same parity. Am I right, sir?
Okay. So yes, so irrespective of how it is arranged, the parity still remain the same.
Yes, sir.
Okay, so we can leave it as that. So R4 is symmetric because anytime A is related to B, every time an integer is related to another integer due to their parity,
Yes,
if we
sir.
reverse the order, the parity is still preserved. So they will still have the same parity, right?
Yes, sir.
Good. Then the last property. So we've seen two properties already. The third
Yes, sir.
property is transitivity. So transitivity, it is something that goes with three uh, elements of the domain. So transitivity is saying if A is related to B, and it must happen that B is related to C before you conclude. Then you must have that this first one is related to the last one. Okay?
Yes, sir.
Before we continue, I remember I used an example in the beginning about uh, relations in terms of siblings.
Yes, sir. Yes, sir. Yes, sir.
So in a family, relationship in terms of siblings, is it symmetric? Is it reflexive in terms of just siblings?
It is, sir. It is.
Can you explain why it is reflexive?
Okay, let's say we have I I am my brother's brother. My brother is my brother. Something like that.
That is the way to explain it. Okay. So
Yes, sir.
if I am a sibling to my brother is also a sibling to me.
Yes, sir.
Okay. So is
Yes,
it
sir.
symmetric? Oh, wait. You just explained symmetry. What about reflexive? Is it reflexive?
Okay, let's see. Yes, sir. It is. It is reflexive.
Are you sure? Are you a brother to yourself?
Oh no, sir. It is not reflexive.
You are not
It is
your
not.
your you are not a sibling to yourself. You are yourself.
Yes, sir. Yes, sir.
So well, that is up for debate anyway. But in normal terms, I don't think it is reflect, but it is symmetric. Okay.
Yes,
So
sir.
in terms of transitivity, it is transitive because if there are three of you in your family,
Yes,
if
sir.
you are a sibling to the second person and the second person is a sibling to the third person, you are a sibling to the third person,
Yes,
right?
sir. Yes,
Let's
sir.
now talk about it in terms of
Set.
seniority. If I'm still talking
Okay.
about family, so firstborn, secondborn, and thirdborn. So if we are looking at so A is related to B if A is younger than B in your family. Well, I know you are the only child in your family, so you might not
Your voice
be able
network is.
to younger than B. So is it reflexive?
I couldn't get that statement, sir, because the network was breaking when you
So
were
I'm
saying
saying
it.
if we are going back to the family again and we are looking at relationship in terms of who is younger than who. Okay,
Okay.
so A is related to B if A is younger than B. So is it
Okay.
symmetric? Is it reflexive?
It is not reflexive.
It's
Because
not
me being
reflexive.
older than you, yes,
Yeah.
sir. If I'm older
Is
than you,
this
then you cannot be older than I am.
yes? Is it symmetric? The same thing. It's not symmetric. Then
Symmetric, yes,
transitive.
sir.
It is transitive because if A is younger than B and B is younger than C, automatically A is younger than C.
Yes, sir.
Okay. So let's go
Yes,
back
sir.
to our usual R1 to R5. Let me write it here now. So R1 is when which one is R1? R1 is
A less than B.
A less than B. So A R1B if A is less than B. A R2B if A
A
plus
plus.
B is greater than or equal to 5. A R3B if and only if A equals to 2B. A R4B if and only if A and B, so parity of A is equal to parity of B. Then I introduce R5 if and only if A is less than or equal to B. So we have seen reflexivity, we have seen
Symmetricity.
symmetricity, and we are now looking at transitivity. So reflexive, we said no, it's not reflexive. Symmetric, we said
Yes, sir.
no, it's not symmetric. What about the R2? Reflexive? No, it's not reflexive.
It's not reflexive, yes, sir.
Symmetric, is it symmetric?
No, sir.
Uh,
A plus B greater or equals to 5. Let me use example first. Let's say A plus B. Yes, sir, it is equals to it is.
addition is commutative.
Yes, sir.
So if A plus B is greater than or equal to 5, B plus A must also be greater than or equal to 5. So it is
Yes, sir.
symmetric.
Symmetric.
AR3B, is it reflexive?
It is not reflexive, sir.
It is not reflexive because A is not equal
Yes,
to 2A.
yes, sir.
Is it symmetric?
No, sir.
No, it is not symmetric. R4, is it reflexive?
Yes, sir.
It is reflexive because parity of A is equal to parity of A. Is it
Yes, sir.
symmetric?
Yes, sir.
Anything that has to do with equality is always going to be symmetric because anything that has to do with addition and anything that has to do with equality will always be symmetric. So this is symmetric. Then is it then R5? Is it reflexive?
Yes, sir, it is. It's reflexive. It's
Then is
also
it
symmetric.
symmetric?
Yes, sir.
Uh,
A less than or equal to B less than. No, B can never be less than or equal to A. So it's not equal. It's not symmetric.
not symmetric. Adams, can you hear us?
Yes, sir. Yes, sir. Yes, sir.
Okay, very quickly, I'm going to do a brief recap of what we have said so far. So that Zacchaeus can also recap what we have, can recall what we have said. So we're dealing with relations.
Okay, sir.
Even from the name relations, you are looking at the relationship between two sets. So it can be a set and itself, it can be a set and another set of objects. And it doesn't have to be a set of numbers, it could be a set of families, set of countries, set of football clubs, it could be anything. And it is a set, and that set is a subset of the Cartesian product. Do you know what Cartesian product means?
Yes, sir. I know.
So relation R is a subset, a relation on A, for instance, just A is a subset of Cartesian product of A with itself. Okay? But generally a relation is a subset of a Cartesian product of two sets. So the example I started with is if we have 1, 2, and A, B, C, if this is our A and this is our B, can you tell me what the Cartesian product is? What is A cross B?
The set of 1A, like into brackets. The set of 1A, 1B,
Mhm.
1C, 2A, 2B, and 2.
Channel scholar. All right. 1A, 1B, 1C, 2A, 2B, 2C. Good. So any subset of this is a relation, and function is putting a restriction on that subset. Okay. So that is a relation. And this is a very simple example. The sets themselves can be very large. Okay, you can have a relation on a set of integers, which was the next example that we used to build this relation. So we are dealing with R on integers, and we are saying A. So our R1 is defined to be two sets are set to be two elements of Z are said to be related if A is less than B. So can you give me two elements of R1?
Is it like any element in the integer?
Okay, before we continue, let me go back again to something. So when I say an element of, so these things, this pair, this ordered pair are called
Yes,
elements
sir.
of relation. Are you with me? Okay.
Yes, sir.
And
Yes, sir.
and we did an example. Okay, let me go back to that example if I still have it here. So 2, 3, 4, 5, 6, 2, 4, 6. 2, 3, 4, 5, 6, and 2, 4, 6. So this is A and this is B. Zacchaeus, I hope you are not annoyed that we are going back.
No, sir. No, sir.
So if we want to write the Cartesian product of this, how many elements are we going to have? Do you know?
5 times 3 and 15.
That's going to be 15. Okay.
Yeah.
So, but we said relation is a subset. So if we define a relation on A and B to be such that A is related to B, if and only if A is less than B, can you list the elements of the relation?
Sir?
Can you list the element of the
Okay.
relation defined as follows?
Okay, sir. That's 2, 4,
2, 4,
2, 6,
2, 6,
3, 4,
3, 4,
3, 6,
3, 6, My hands are even faster
4,
than your
6,
mouth. 4, 6,
4, 6. I can hardly see the screen safe. It is lagging.
Oh, okay.
And 5, 6.
5, 6. Is that all?
Yes, sir.
Okay. So 2, 4, 2, 6, 3, 4, 3, 6, 5, 5, 4 cannot be there. Then we have 5, 6. Good. So what is the domain of this relationship? Of this relation?
That's the 2,
Mm-hmm.
the set of 2, 4,
3,
5.
4, 5. What about the range?
4, 4, 6.
4, 6. Thank God you don't make the same mistake. Okay. What about the inverse of R?
Inverse of R. 4, 2.
Good.
6, 2.
Good. So it means you know it.
3,
So I don't need to, we don't need to spend time defining that. Then the next thing we now talked about are the properties. That is where the fun begins. So we have some interesting properties of relations. we have reflexivity, we have symmetricity, we have anti-symmetricity, and we have transitivity. Do you know what they mean? Adams, do you know what each of these mean?
I happen to I checked it through, but I forgot it actually.
Okay, let's talk about it. That's where we are. So reflexive means a relation is said to be reflexive. R is reflexive if A is related to A for all A in the domain. So when you look at any set and you look at the definition of the relationship, if every element in the set is related to itself, then we say that relation is reflexive. This example here that we just did, is it reflexive?
A quick question, sir.
Okay.
Let's say set A, this set
Yes.
the relationship on set A, we are not looking at the B, like the relationship on set like that.
Yes.
I
Yes.
don't know how do you do it.
Well, it is just a subset of A cross A. So it depends on what you are defining it on. We are going to see an example integers now. Okay.
Okay.
So this example, is it reflexive? This relation that we have, it is not reflexive because we don't have 2 2, we don't have 3 3 or 4 4 or 6 6 or 5 5. So it's not reflexive. But if we now bring it back to the set of integers, so that is why we've defined those 4 things that we have here. Let me clean this. Láago mélòó lorún tí ń kùn ẹ́?
No, Okumi. Mo ti jẹun. All class.
All right. So for R1 is defined, A is related to B under R1. So we are talking about relationship on integers now. A is the set of integers. Okay. So we are looking at elements of integers. So A is related to B if and only if A is less than B. So can you give me 3 examples of elements in R1?
Minus 1 1.
Minus 1 1. What you more will?
I have 1 2 also. And maybe 1 3, something like that.
1 3 and so on and so forth. So all these are in R1. Beautiful. What about when we define R2 if and only if A plus B is greater than or equal to 5? Can you give me examples of elements of R2? Again?
Hey, wait, hold on, sir. Greater than or equal to 5.
Yes.
Yeah, 1 4.
1 4.
You can have minus 1 6.
Yes.
You can have maybe 1 5.
Why
and 4
do you
itself.
why do you like 1? 7 2 is in R2. 195 minus 3 is in R2.
Yeah.
You have
exactly. It's greater than or equal. Just like stay in back.
Okay, so we are just looking at two numbers, two integers that when you add them together, you get something that is greater than 5. All right, R3.
Yeah.
A is related to B if and only if A is equal to 2B. So can you give me examples of elements in R3?
As 2 and
So 2, 1, good. Uh-huh. I couldn't hear you. What is that?
4, 4, 2, 4 and
4,
2.
2. You like small, simple numbers. Uh-huh.
Okay, let's do 10, 5.
It's still small, but it's okay. R3. So if R4 is related to B, if and only if A and B have the same parity.
What is parity?
Even, odd.
Even odd number.
Yes, parity talking about whether the number is even or odd. So can you give me examples?
That's 1, 3.
One,
Okay, 1 is not there. No. 4,
uh-huh.
something like that.
2, 4,
As we have 7, 9. No,
7,
7,
9,
7.
so on and so forth. Then
Yeah.
finally, if and only if A plus B is, let me change it to less than or equal to 5.
Less than or equal.
Or
Yeah, all this like that. 1,
wait,
4.
that's not the R5 we defined. A is less than or equal to 5. That is the one we defined. Sorry, A is less than or equal to B. Yeah. So can you give me an
Yes.
example?
Is as minus 1, minus 1, 1. That's 1, 1. We can have 1, 1, 2, 2, 2.
Yes.
So all those stuff.
Good. So let us now come back to the properties. Reflexivity. Is R1 reflexive? From what we defined.
Almost.
So is R1 reflexive?
No.
Why do you think it is not reflexive?
It's very reflective as how a it's reflective. I
I
don't get the
can't see.
definition, sir.
Okay. So
Yeah.
reflexive, a relation is reflexive if for every element in the set is related, the element is related to itself.
Okay.
So it's R1 reflexive.
Because you're having two different things that's related to each other.
No,
Abi?
just one for every element. So A must be related to A for all A in A. That is when we say that R is reflective.
Boy down,
So
time too low.
is can you have 2 to be related to 2 in R under R1? Adams. See here?
I don't know.
I don't think it's. Can you hear me, Adams?
I don't think it's here.
The network is really low. All right, so
Yes.
let's fill it again as I don't, but I think you understand it. So let's just move on to the next part. So that we don't waste your own time as well. So the last one that we've not talked about is antisymmetric. So when is the relation said to be antisymmetric? So antisymmetric means that the only time we have A related to B and B related to A, then that means A and B are actually the same. That is the only time you can have both of them. That's the meaning of antisymmetric. If you have A related to B and B related to A, you must have A equals to B. Okay?
Yes, sir.
So let's look at R1. Is it antisymmetric?
No, sir. There's no equal to be there.
It's not Are you sure it's not antisymmetric?
Yes, sir. We have one. I'd not write down the what's it called, the sets. But we don't have the only time it can be symmetric is if A is equal to B, and for that R1, we don't have any A that is equal to B there.
Okay, good. So it is not antisymmetric. Give me a second to think about that. So A is related to B and B is related to A implies that, okay. So assuming it is less than or equal to, then we can have that. Good. What about R2? Is it antisymmetric?
Yes, sir, it is. We have less than or equal to.
I'm talking about R2. So is 2, 3 in R2?
No, sir.
Yeah. This is R2.
The thing is, I don't write down the what's it called, those numbers.
You don't need to write down those numbers. This is the only thing that it is important. You are talking about integers. Okay, R2 is described to be such that when you add A plus B must be greater than or equal to 5. So it's 2, 3 in R2.
2,3 is in R2, yes, sir.
Is 3,2 is 3,2 in R2.
Yes, sir.
So both of them are in R2. But is 3 equal to 3 and 3 equals to 2?
No, sir.
So it is not antisymmetric.
Okay, sir.
Do you understand antisymmetricity now?
Yes, sir. I get it better like this, yes, sir.
So antisymmetricity is saying anytime we have A is related to B and B is related to A,
then A is equal to B.
Must be equal. Okay?
Yes, sir.
What about R3? Is it antisymmetric?
Equals to, let's see, 2, that's 4 and 2. Now, it is not, sir.
It is not.
Yes, sir.
Okay.
Yeah, it's not.
Good. What about R4?
R4, yes, it is antisymmetric. And I have two to them. Course be yes. Actually, we have 2 and 2. 2 and 2 are
what
the same parity.
What about 1 and 3?
1 and 3 have the same parity, but they are not equal. But I used 2 and 2. But for 2 and 2, 2 and 2 works.
That's why I told you that to prove that something is true, you cannot use one number.
Okay.
So you can only use counter example to prove that something is not true. Okay. And that
Yes,
is why
sir.
sometimes when you are faced with a question of to prove or disprove, first thing you should try to see is look at simple examples to check whether it will fail, not whether it is true.
Yes, sir.
So if you cannot think of something that makes it false, then you can now start thinking of, okay, how can I prove it to be true? That is the general way to think about proving. So when you are faced with a statement and you are told to prove or disprove, the first thing you need to think of, is this thing actually true? Can I think of easy examples where it is false? Then if you cannot think of there could be, but if you cannot think of it, try to now prove it. If you are now facing problems with proving, then it means maybe you have not thought so deeply about why it is false. Okay?
Yes, sir.
So look at the definition of antisymmetricity again.
So,
A relation R is called antisymmetric if anytime A is related to B and B is related to A,
then A equals
A
B.
must be equal to B. So when we look at that of parity, 1 is related to 3 because
Yes, sir.
they have the same parity. 3 is related to 1 because they have the same parity, but 1 is not equal to 3, so it's not antisymmetric. What
Yes,
about
sir.
we have already
Alpha.
talked about this. What about set inclusion?
In R5.
No, set inclusion generally as a relation. So RS. Do you know the meaning of set inclusion? When I say set inclusion, I'm saying A is related to B if and only if A is contained in B.
Oh, so can
So
say
let's start with reflexive. Is this reflexive?
if A is a subset of B, then B should also be a subset of A.
That is not
Since A,
that is not reflexivity. Is it reflexive?
yes, sir.
Explain to me why it is reflexive.
Okay. So we have for reflexivity, that for all A in A. Since A is contained in B, are
We
you
are
with me,
not
sir?
looking at B. When we are dealing with reflexivity, we are dealing with only A.
Okay.
So reflexivity means, this is the definition. A is related to A for all A in A. In this case, for set inclusion, we are looking at the set of all sets. So to check whether this relation is reflexive is to ask yourself whether a set is a subset of itself. And is that true?
Yes, sir.
Every set is a subset of
Yes,
itself. Every set is contained in itself. So it
yes,
means
sir.
it is reflexive. Do you understand?
Yes, sir.
Is it symmetric?
Between A. Yes, sir. It is A in
It
B.
is not symmetric. If A is contained in B, B cannot be contained in A. The only way that is true is when they are equal. That is so. It means it is antisymmetric, but it is not symmetric.
Because sometimes they will say A is a subset of B, so B is also a subset of A. When you're proving all these little proofs.
So the only time that occurs, the only time we can say that is when we want to show that A is equal to B, and that is antisymmetricity. Okay, so if this is A, or let's say this is B and this is A, this is what it means to say that A is contained in B, right?
Yes, sir.
So it is not symmetric because we say symmetricity is not that when it happens once. Symmetricity means for every time it happens. What am I saying happens? For every time A is related to B,
B is
B
also
must be
related to.
related to A. So, and in this case, A is related to B if A is contained in B. Okay?
Yes, sir.
So even this diagram has showed us that in this case, we cannot have B is contained in A. So it means it is not symmetric. Do you understand?
Yes, sir. I'm with you, sir.
What about transitivity? Is it transitive?
Positivity.
So let's
No,
remind ourselves what transitivity means. Transitivity means if A is related to B and B itself is also related to C,
A. Okay, to C,
then
yes.
A is related to C. So is this relation of inclusion transitive?
Let's say A is in B and B is in C. It means that A is in C. Yes, it's transitive.
It is transitive.
Yes,
Let
sir.
me bring another relation. Relation of perpendicular lines. So a line 1 is related to line 2 if and only if line 1 is perpendicular to line 2. Is it reflexive?
Line 1 is perpendicular to line 2 means like it's perpendicular to line 1. Line 1 line 2. Line 1. No, sir, it's not.
Why is it not reflexive?
We are only dealing with the first element, line 1. For the
Yes.
for reflexive, we are always dealing with the first item.
Yes.
We have line 1. Line 1 is only perpendicular to line 2. Line 1 is not perpendicular to line 1.
Good. That don't beat around the bush. That's what I have been expecting since. Line 1 is not perpendicular to itself. Any line is not perpendicular to itself.
Yes, sir.
So it is not. So it is not reflexive. Is it symmetric?
Okay, let's line 1 perpendicular to line 2. Line 2 perpendicular to line 1. Yes, I think symmetric.
It is symmetric
Yes,
because
sir.
anytime two lines are perpendicular, you can switch it. What about transitive?
I want to go down line 2, line 2. Line 1 is perpendicular to line 2. Line 2 is perpendicular to line 3. Then line 1 is perpendicular to line 3. Yes, sir. It's transitive.
Are you sure?
Line 1 is perpendicular to line 2. Then let's say line 2 is perpendicular to line 3. Yeah, it means line 1 is perpendicular to line 3. Yeah, it is.
You're not thinking about it.
Let me
let me
let me
draw. Let me
let me,
draw. Let
let
me
me think
draw.
again.
Let
Let
me
me think.
draw line 1, line 2, line 3 for you. Line 1, line 2, line 3. Can you see what I'm doing?
Yes, sir.
Line 1 is perpendicular to line 2, isn't it?
Yes, sir.
Line 2 is perpendicular to line 3, isn't it?
Yes, sir.
Is line 1 perpendicular to line 3?
No, sir. They are parallel.
So it is not transitive.
Transitive.
Okay, so these are the beauty of of abstract mathematics. So you have to
So this is headache. You have to think.
exactly. But you get to a point where you'll be able to see these things without thinking too deep. Okay, that is the beauty of studying mathematics. It sharpens your deductive reasoning skills. All right, so line 1 is perpendicular to line 2, line 2 is perpendicular to line 3, but line 1 is not perpendicular to line 3. Is it
Yes, sir.
anti-symmetric?
No, sir.
No.
Yes,
So
sir.
we have line 1 perpendicular to line 2, line 2 perpendicular to line 1, but line 1 is not the same thing as line 2.
Yes, sir.
Then what about if we do parallelism instead? Line 1 is related to line 2 if and
It's
only
line
if
1.
line 1 is
Line 1.
parallel to line 2. Is it reflexive?
Okay. Line one is line one is it is parallel to itself. Line one,
Good.
yeah, parallel. Yes. So it's
Is it
reflexive.
is it symmetric?
Let's see. Line one is parallel to line two. Line two is parallel to line. Yes, it is symmetric.
Is it transitive?
Let's see. Let's see. Okay, let's see line one, line two, and line three. Line one is parallel to line two. Line two is parallel to line. That means line one is parallel to line. Yes, it is. It is, sir.
There's no hidden trick hidden this one. Then is it antisymmetric?
Yes, sir.
It is not.
Sir, it's not okay.
Line one and
Line,
line three in this red diagram, are they the same?
no, sir. It's little mistake, sir.
Line one is parallel to line three, and line three is parallel to line one, but line one is not equal to line three, so it is not antisymmetric.
Yes, sir.
Okay, so that's just the beauty of. So we've seen the
Relation.
reflexive, because I want to wrap it up for now. Reflexive, we've seen symmetric, we've seen transitivity, antisymmetric. So there are a lot of examples, the ones that I even sent to you. Some, I think,
I would submit
my
tonight.
status. Okay, good.
I'll
So
tonight, yes, sir.
we'll cut it tonight. Then, so before we wrap it up, a relation that is reflexive, symmetric, and transitivity is called an equivalent relation. Okay?
Yes, sir. So
And
all
a relation,
that if it satisfies all the
so if it satisfies reflexivity,
all the
symmetricity, and transitivity, all of them, none of them must fail. All of them, then it's an equivalent relation. And a relation that is reflective, antisymmetric, and transitive is called an ordered relation.
that relationship. That relationship.
Good example of ordered relationship is, let's see, will be R1. Oh, it's not antisymmetric. It will be R5.
Alpha, yeah. Alpha,
So
yeah.
we said A is related to R5 if and only if A is less than B. That is exactly what we call ordering. We are ordering it, and we are looking at what is bigger than what. That is ordering. So this is ordered relation. An example of equivalence is anything that has to do with equal things. So, for instance, the one of parallel lines, yes, is equivalent. The one of the same parity, is equivalent, and so on and so forth. Okay?
Yes, sir.
So that should kickstart your adventure into reflection. I mean, relations in general. So you try your hands on some of the exercises that you already have from here. And the next time we are able to meet, we'll look at. So this is just what we said: equivalence
Yes, sir.
relation, and
That's how.
yes. So when it's just you have to, because it's not just numbers, unlike
Yes, sir.
the one we just said on integers. Or maybe we should do one of the proofs for you to see what I'm talking about. So let's see. Let's see this number 3.
Okay, sir. Is equal to B. I must be question.
Let's look at this number 3 and end it there. So consider the sets of natural numbers and relation on n given by. So we are saying A is related to B if and only if A minus B
Must be
is a
equals
multiple.
to
I think this
3.
question is in one of the exercises I gave you before. Yeah. If you look at, yeah, I'll go and quote it after this class. So can you give me an examples of elements in this relation?
Let's say A is 12, and then B is 3.
Yeah. So 12,2 is in R,
So
right?
12,
Can you give me another? Can you give me another one?
12,3,3.
Comma 3 rather. Sorry. Can you give me another one?
Yes. So we have okay, let's use negative number now. Negative 2, negative 2 here. Negative 2 and then negative 2, negative 1. It's negative 2, negative 1, negative 2 minus, no, negative 2 and 1 rather.
What about
Network. Negative
this?
2 and 1.
Yes. What about this? Is it in R 5,11? Is it in R?
Yes, sir. It is.
Why?
5 minus 11 is negative 6. We can make it as b into bracket negative 2.
Beautiful.
That k is negative
2. Good. Now let us show that it is an equivalent. So to show that it's an equivalent relation, so we need to show that R is reflexive,
yes,
symmetric, and transitive. So A is R reflexive?
12 3. No, sir.
It is
12 3 3
reflexive.
12 3
So
3 12.
how do we prove it? So observe that A minus A is equal to what?
That's 0. Or
0. But 0
yes,
is what? 3 times 0.
Ah.
And 0 is Z.
Yes, sir.
So this implies that A is related to A. Therefore, R is reflexive. That is how to show reflexivity. Okay?
Yes, sir.
Then symmetricity. How do we show this symmetricity? So we assume that A is related to B, right?
Yes, sir.
What does that mean?
It means that or this
Definition.
implies that
It means that A minus B is equal to 3K.
okay from the
Right.
question given. Yes, sir.
But do you agree that that means that B minus, what is B minus A?
also be minus it will be equals to minus 3k.
Negative 3k, which is equal to 3 times L,
Minus okay.
where L is negative k. Does that make sense?
Yes, sir.
And what does this mean? This means that B is related to A. Therefore, R is symmetric.
Sure.
The one that is usually a little bit tricky is transitivity. But let's try. So what do we need to show that transitivity? Let's write it here. What do we need to show?
One, if A is related to B and B is related to C, then A is related to C.
This is what we want to show. So we have to, what do we have to assume? We have to assume that A is related to B and B is related to C. Right?
Yes, sir.
So, and what does this mean? What does our assumption mean?
This means that A is related to B is related to C.
According to the definition, what does it mean for A to be related to B? This is the definition.
A minus B equals 3k.
So this implies that A minus B
B
equals
3k.
3k and what?
B minus C equals 3, let's say 3L.
3L. So what do we need to show? We need to show that A minus C is 3 times something.
Yes, sir.
So what do you think? What do you think we should do?
We can make B the the formula from the first one. So B will be equals to A minus 3k and then plug it in the second one.
Good. That's one way to look at it, but let's go with it. So let's say this is star and this is star. From star, B is equal to A minus 3k, right?
Yes, sir.
So substitute A minus 3k
Into
for
star.
in star. That means that we're going to get A minus 3k minus C equals to 3L.
So A minus C. A minus C equals
3
into brackets plus L. Yeah. So
which is equals to 3M.
Yes. Where M is equal to K plus L.
A is related to C.
Sharp.
Therefore, R is transitive. Combining A, B, and C that R is an equivalence relation. It's always fun showing equivalence or other relation. So we're going to end it here today. And go and practice with other questions that you have. Yeah. Welcome. So I would get this video posted on YouTube so that you can revisit it anytime you want to record. Any question before I end that?
No, sir. Just those questions. Maybe you help me forward them, and I'll solve them. And then
I will go and quote them because we have done them before. So I'll quote. I have sent it to you before. I will just quote them.
Yes, sir.
All right. Enjoy
All right,
the
sir.
rest. Yeah. Bye.
You too, sir. More power to you, sir.
Thank you.
All
You
right,
too.
sir. Sir.